Okay, so let's start. So today we're gonna talk about divide and conquer again. It's the last class on divide and conquer, and next class is gonna be dynamic programming. Okay, so the problem that we're gonna look at today is another fundamental thing, which is just a selection problem. So what is this problem? Basically, just imagine that you have some tournament on like in the sport, or basically you just want to compare which team is the best, or in other words, think like each team as a number, and you want to find out which one is the best. So the first question I want to ask you is like if you have, let's say, n many teams, how many comparison you need to do just to find out which one is the best? Or in other words, you have n numbers, how many comparison you need to find out which one is the minimum?
Yeah. n-1.
Yeah, exactly. How do you do that?
You can do it any number of ways. Like you could just have like one team, and you could keep comparing each team, and whichever team like wins, it stays.
Exactly.
Like,
good. Very good. So n-1 is enough to find out which team is the best. Can you do better than that? So anyone who thinks it's not impossible? Or it's impossible? Yeah.
Yeah, I mean, if it's like all random, then I don't think like you have to compare everything, right? If you don't know anything about like the data.
Yeah, like so the answer is yeah, like you shouldn't be able to do this better than n-1 because as long as you have less than n-1 comparison, there will always be one team that is not even participated in your comparison at all. So you know nothing about that team, and that team might be the best. So n-1 is the best you can do if you can only compare two teams one by one, like two teams. If the operation you have is just comparing two teams. Okay, good. So n-1 is enough. But okay, a nice puzzle is, okay, what if you want to find the second best team? How many would be enough? How many comparison is enough?
Still n-1 because you need to know what the first best team as well as you need to know the first best team and the second best team at least, and every team needs to play at least once just to be able to know how good they are.
Good. So like what you say is that n-1 is something that you need for sure, but it's not clear you can find out which one is the second best in just exactly n-1 comparison. Can you do it in 2n? You can, right? Just find out the best guy first, and then whatever, like just throw out that one, find the second best. So 2n is good. But actually there is a way to do it better than that. Actually, n plus log n is enough. Anyone have ideas how to do that?
If you have a single elimination tournament, you can take like the team that was in the final but didn't win, and then like compare them to all the teams on the other side of the bracket in a way, because those are the only teams that could potentially be better than them.
Good. So let me just repeat. So you know that the second best team will just always win until it compete with the best guy. So you know that like the second best guy is always just among the team that lose to the best guy. And now if you do this kind of single elimination, and let's say that this guy is the best, and you just keep looking at the team that lose to the best guy. How many teams are there? It's going to be just log n because the depth of this tree is log n, right? So you just find out the maximum guy among the log n many guys that lose to the best team. Make sense? Okay. Good. So that's about the best team, second best team. How about like the third team or like any team? Like so now the problem is just let's say that you have n numbers or n elements that can be ordered. You want to find the k smallest element for any k, right? And the only operation you can do, let's say you can only compare two elements, and that's just count as one operation. We want to know how many operations you need to do. Okay. So of course, like if you want to find the k smallest element, you can do it in OK time, OK comparison. Just find the best guy, throw it out. The next best, throw it out. So ONK operation. Yeah. Can you do it in n log n for any k? Yep.
Sort the list and then log n time and then find the k smallest element.
Yeah, exactly. You can first sort the whole list, and that takes just n log n comparison. The way to do that, there are many ways. You can do quick sort, you can do merge sort. So that just take n log n operation comparison. And once you have this list sorted, you can just go through the list for any k in linear time. Good. So n log n is enough, but yeah, but that like kind of basically gives you everything. But now the question is, if you just want one guy in the list, the kth guy in the list, can you do better? And what we're gonna show today is that you can do it in just ON for any k. It doesn't matter what k is. Okay. So that's and the algorithm is so simple actually. And the reason that it's so simple is that because you have randomization. So today we're gonna see like the first example why randomization is like a powerful. Okay, again, the problem is you have a set S, you want to find the k smallest element. And now, before going to the algorithm, let me define one thing. For any element E, I said the rank of E is just like the position of E when you sort the list. Okay, so to find out for any fixed element E, you can find out the rank of E just by doing like n-1 comparison. And how to do that? Well, given this given a list here, you have E. You can just compare E to everyone, and then you will get like the guy that is less than E, and the set that is more than E. And now you can just from this thing, you don't know the order here, but you know how many of them is less than you, so you know the rank of E. Good. So now the algorithm is, now let me present the algorithm. The algorithm is just here. First, I'm just gonna pick a random element E. This is where like I use randomization. Just choose a random guy. Then I compute the rank of E, and that gives you like the guy that is less than E and the guy that is more than E. Okay. Now, if the rank of E is exactly K, I use R to denote the rank of E. If R is exactly K, then you are done. You are lucky. You just finished. But if not, then there is a clear way to do divide and conquer. That is, okay, if E is more than what you want, that is if the rank of E is more than K, then you know that the kth element is in this set, S less than. So well, just recursively solve the problem in S less than and you want to find the kth element in this set. Otherwise, you know that what you want is in this set, k s more than. So what you do is you try to recurse in s more than, but the rank, the element that you want to find now is not k. You need to shift it a bit by k minus r, right? Because you know that like you have eliminated r many guys here already. So if you want a case guy in the whole list, you better get like k minus r guy, the k minus r element in this part. So it should be quite clear that this algorithm like, is correct, at least. Like it's really just do it, like the correctness is quite straightforward. The question is just that what's the running time of this algorithm? Okay, before I analyze the running time, question about the algorithm. So this is the randomized algorithm. So what we're gonna analyze is the expected running time. The running time of this algorithm is a random variable, right? So the first thing you need to know about this random variable is the expected value of it. So let me denote kn to be the expected number of comparison made by this algorithm. And now to analyze this, we need to like write down the recursive equation, and it led us to something quite complicated. But let's go through it. Okay, so first, what's the running time? Like, what's the number of comparison that is made by the algorithm? Well, first you need to you pick an element e that's just constant time. But once you pick e, you compute the rank of e. So that takes n comparison. So that this is this part. And if you are lucky, e is the one that you want anyway. You're done. But you might not be lucky. And now we need to like compute the expected time you need to spend if you're not lucky. How many cases are there? Like there are n-1 case because there are n-1 cases where e is not the case guy. So you just sum up all the cases and then average that by the number of cases. Okay, so this is like the number of cases. So you average them out. That is multiplied by 1 over n-1. And and now let's count the total number. Like let's count all the cases when you are not lucky. So this sum just count all the cases when k is less than r. Okay. So okay, good. Or when k. Yeah, when k is less than r. Yeah, when k is less than r, like what you want, k is actually less than the rank of e. In this case, you recurse in s less than, and that have size at most r, right? And that's why you get this term. And how many cases are there? It's just all the case when r is more than k, so you just sum up from r equals k plus 1 to n-1. Yep.
With the original algorithm, why for the k is greater than r case does it subtract k? Why does it do k minus r for the recursion?
Okay, good. So let me answer that. Well,
Isn't k the target element? So
yeah, k is a target element, but now let's say that you look at the first element in this list. What's the rank of this guy? It's r plus 1. Okay, so you need to shift what you want. Okay, so let's come back to this analysis. Right, so this is just summing up all the time that you might need to spend when k is less than r. And then you just do the same when r is less than k or k is more than r. So just sum up all the cases when r is less than k, right? In this case, we're gonna recurse on the other side, which is s more than. The size of that list is n minus r at most. Right, and the rank that we're gonna recurse is k minus r as well. Okay. So once you sum them up, you just average that, and that's how you get the expected value, expected running number of compression. So question about this recursive equation, although it's look complicated, like question about the interpretation of this. Good. Okay, now now we have something that we need to analyze. It looks complicated, so the way to do that, the way to analyze it is to simplify things by trying to analyze something that is an upper bound of what we need to analyze. Right? We just want an upper bound. So if we can analyze something that we know is worse, but it's easier to analyze, that's okay. So the idea is that, okay, let's try to analyze a different process where you just assume that you always recurse on the bigger side of the set. Okay. If you assume that, you can actually forget about k. It doesn't matter what k is. Anyway, you're going to recurse on the bigger side. And if you do that, now let this thing, like q of n, be the expected number of compression of this process where you do the same thing, like you pick random element, but now you recurse on the bigger side, always. Right? So what you do, you have the same number of compression here, but in the sum here, right? What happened is that you just take the maximum number of this thing because you go to the maximum, the larger side. Okay. There are all the cases where r is 1 up to r. R is actually r is n minus 1. Yeah. And then you just take the larger one out of this. Okay. And then once you sum them up, this thing up, then it just means what? It means that you just sum up like when r is less than n over 2, you just take the bigger side. When r is more than n over 2, you just take the bigger side too. So it means that it's always just sum the term that is always at least half. But the term that is at least half, you sum it twice. So that's why you get a factor of 2 here. Make sense? Good. Now this looks kind of simple enough now. So it looks simple enough, and we're gonna just analyze that. We try to prove that Q of n is linear. That is O of n. And to prove that it's O of n, what we need to do is we basically need to show that there is some constant c such that Q of n is at most Cn for all n. Okay. And you will see that I kind of need to name the constant c here for the proof of for the induction proof. This is going to be important, and you will see soon. But let's now prove for induction on n. Well, the base case is easy. I will just set like a C to be like a maximum between Q of 1 so that the base case holds between this thing and some number 4. Like it just need to be big enough, and you will see why I choose this to be like at least 4. Okay, but just set it to be some constant that is big enough. That's fine. Now for the induction case, well, what you have is that this should be n-1. What you have is that like you by induction hypothesis you have that Q of n now is at most Q of n prime is at most Cn prime for all n prime less than n. So we can just gonna use this induction hypothesis. How? Well, just write down this thing, this equation that we have before, and now like just apply induction hypothesis here. Okay. Q of r is at most CR. And once you have that, it's just now about calculation. You start like the way to think about it is that okay, this is a sum from basically the sum from n over 2 to n minus 1. It looks like something that it looks like something like n squared, right? But you just need to calculate that, and you get something up to here. Like this looks like something that is n squared. It now is divided by n. It must be divided by n. So you know that at the end, this term here need to look like something like order of n. But you need to calculate it a bit. And now, at the end, you get to like you simplify the calculation. And at the end, you need to show that your final calculation need to be less than Cn. But you see, like the last step here actually will be true only when C is big enough, at least 4. For example, if C is 1, let's say that you just choose C to be 1. This is not good anymore. Why? Like if C is just 1, then this is just n, and this term is already something like n to the 7.5, right? So this is like a n times something bigger than 1. It cannot be less than n. So you see, like you will like just from the calculation, it will actually force you to choose the constant C in your induction hypothesis to be big enough. Okay. But if C is at least 4, then everything works out. Okay. So let me like stress a bit like that fixing some constant in the induction hypothesis is important because let me tell you like some wrong proof. Suppose that I want to say now that like a Q of n is linear, and some proof that looks okay but actually is wrong is here. We have this equation, and then just by induction hypothesis put QR to be O of R, and this sum looks like n squared, O of n squared. Divide this by n, you get O of n here, and that looks like On. So it gives you the correct answer that you want, but what's so wrong about this, right? Well, it can be really wrong because let's see another example. Let's try to analyze Tn, this equation. We have seen this before, and we know that this is T of n is n squared. It's not less than that. But let's try to prove that T of n actually is O of n by induction. Well, I can say that, okay, T of n is 4 times t of n over 2. So that's like O of n over 2. And then plus n. But that's On, right? So like now something must be wrong. So what is wrong is that this is because like you can actually hide some constant here, and then like it's not actually the same constant that you get at the end. Like if you try to put some constant in here, actually you will not some specific constant C in the induction hypothesis. Actually, you will find out that there is just no constant that make it work ever. But the big O notation kind of hide that, and that's why you get something wrong. Okay. So now, let's get back to this quick select algorithm. What I have shown is just that this quick select algorithm takes just O of n comparison in expectation, right? So the expected value of this random variable is good, but can someone tell me that why, like actually in the worst case, this algorithm might actually spend n squared time? Yeah.
If the random number, say your target value is the value with the highest rank, and then your random selection algorithm gives you like the first, second, third, fourth, and so on and so forth. So you end up running the algorithm n times because you keep getting an unlucky random pick.
Exactly, very good. Like every time that you choose a random element, you choose, let's say, the smallest guy. When you recurse, you just like throw out one element from the list and recurse on the list that have one less element. Repeat this n times will give you n squared. So this can be bad, although the expected time is good. Well, the question then, like, is there an algorithm that is that is always linear? And the answer is yes, we have. And that is found out like 50 years ago already by Blum, Floyd, Pratt, Rivest, and Tarjan. And the algorithm is really cute. It's called median of medians. So you see from the discussion just a moment ago, you know that this quick select algorithm is bad when you choose an element E such that it's kind of at the extreme of your list. But then, now suppose that there is a way to guarantee that you have the way to select some element E such that it's kind of close to the middle of the list. If that happens, that is good. Why? Because when you try to recurse, if E is close to the middle, when you recurse, whether you recurse on the left side or right side, the size of the recursion gets shrink by a lot, right? Like if it's at the middle, exactly the size of your problem gets half. If it's not quite in the middle, but let's say like close to the middle enough, it's still good. So that's the idea that we're gonna do. We're gonna see how to select some element E close enough to the middle in the deterministic way. And if that happens, then you're done. Okay. So the algorithm is just here. What we're gonna do is that let's say we assume that k is not too small, because if k is super small, we have nk algorithm anyway, and that's linear. So let's say k is not too small. So if k is small, we're done. And now what we're gonna do is this. I'm just gonna divide the set S into the group of 5. Like this. Make a group of 5. Each group is of size 5. And for each group here, let's say I even sort that, sort this group. The smallest guy point to the larger one, okay? And there is a middle guy here. This is a median of each group. And let S prime is the blue guy. S prime is just contains the median of each group. The blue guy is S prime. Okay. And what we're gonna do, the way to define the element E that I claim it should be near the middle is simply to pick the median of this S prime. E is a median of medians. Well, how do you pick the median? Well, just do it recursively, right? Just use the same algorithm recursively. Okay. Now, is it clear like how exactly E is defined? Okay. Now this is a claim that we want. I want to claim that E, the rank of E is close enough to the middle. Not quite in the middle, but close enough. So why is that? By the way, like, just to say again, everything here is less than this guy is less than this guy is less than this guy, and this guy is less than this guy. So I just draw an arrow from A to B if A is less than B. Question?
Isn't K just going to be a random element for each group of 5 then? Or just like always the 5th element?
Say it again. K is.
It won't, or I guess won't E always be just a random element from each of the groups of 5 then?
No. E is not. There's nothing random here at all. Like we just put it into a group of 5, compute the median of each group, and E is just the median of that group. It's deterministic. Okay. So now, yeah, I claim that rank of E is near the middle. So why is that? So first, okay, maybe let me. First, do you agree that everyone in the blue box here is greater than E, right? We know that everyone here is greater than E, and like, because everyone here must be greater than E as well. And the same thing is that everyone in the red box, except E itself, is less than E. Okay. So all I need to show you is that the box here is big enough. If both of the box is big enough, then it means that E must be close to the middle. And yeah, the claim is that both of the box has size at least 0.3 times S. And how to see that? That's not hard. Well, if let's say I draw this box, this whole box up to here. This is like a 3/5 fraction of the whole thing, right? And the red box need to be like at least half of 3/5. So the red box now have size at least 3/5 times 1/2 times S. And that's like a 0.3 S. And the same argument goes to the blue box. So both red and blue rectangle is big, are big. Okay. Question about this proof.
Why is the whole bottom 3/5 of the total?
Okay, so like there are basically 5 elements here, right?
Oh, I see it.
Yeah, right. So that like three element from 5. More question? Okay. So yeah, now once you get an element E that is kind of close enough to the middle, what you need to do is the same like before. We just do the same trick, the same algorithm like in quick select. Actually, the whole point of using randomization in quick select is just to basically, morally, just to try to get an element near the middle, right? We don't know how to pick one near the middle, but if you choose a random guy, it should be near the middle. Here we just show how to deterministically get the guy near the middle. And once you have that, well, just define s less than, s more than, like before, recurse on the right side of the problem. So is the description of the algorithm clear before we analyze the running time? Good. So let's analyze this, right? Well, first, to compute S prime, let's take linear. Why? Because what we do is that we just sort the number, but each group is of size 5. So that's constant. We do that like linearly many group. That takes O(n). How do you get E? You do it recursively on S prime. The size of S prime is 0.2n because it's just like a 1/5 fraction of the whole thing. And then now you try to recurse and you compute the rank of E, and to compute S less than and S more than, you take O(n) comparison. And then you need to recurse either on S less than or S more than. But because the rank of E, you know that you would throw, you know that both of the sides here can have size at most 0.7n. Right? Because, yeah, the rank of E, the rank, this E is between this fraction. So you know that you would throw away either one side that you throw away will have size at least 0.3. So the side that you recurse recurse is at most of size 0.7. No matter what, it's not going to be worse than 0.7n. So that's why you get this recursion. Okay. And we just need to analyze this recursion. Okay. So to analyze this, we can use the induction. But the way to see that this should be like a linear quickly is that as long as the sum of all these parameters, when you in the recursion, the sum here is less than n by some constant factor, you actually know that it should be linear. But we can do it by induction too. In the best case, just set C to be big enough, bigger than T1. For the induction step, just write down, use the induction hypothesis, calculate and then conclude that this is less than Cn. Okay. And you see again that you need to set C to be big enough compared to the constant, whatever constant you have in the recursion. Once C is big enough, this conclusion will work. In this case, you can check that if C is bigger than C prime by a factor of 10, then you're good. Okay. All right. Now, yeah, we are done with that. We have that T of n is O of n.
Is it faster in the randomized algorithm in the average case?
I don't think it's faster. Like the leading constant at the end is not as good as a randomized one. So, question to you, like, what's so special about number 5 here? Like, can you do it in a group of 7 or 9? Okay. So at least it's really clear to you that the algorithm is well defined. Like if you choose instead of 5 to be 9, you know exactly how to implement that, how to write down the algorithm. Now it's just about analyze that algorithm. And I encourage you to try. Like just the spoiler is that it works, but you should try and see it yourself, just to like play with this kind of recursion. Make sure that you understand this thing. But the question though, what if instead of 5 and 7 and 9 and other thing, what if I choose to be a group of 3? Okay. Now this turns out to be a research question. You can define the median of medians algorithm when you form a group of 3. But if you follow this exactly the same analysis, what you will get will look like the recursion that you get will look like this. That is, this is the time to find E. That is, you recurse in the median of median, but like the size of S prime here is n over 3. And this is when you recurse on S more than or S less than. But you see the sum here. This sum here gives you exactly n, not something that is less than n by a constant factor. And if you solve this equation, you get something like n log n, which is as bad as sorting. But it just means, like, it doesn't really mean that like this algorithm is bad. It means that this analysis gives you this much. Okay. And the research question that people still don't know is that, okay, some people actually conjecture that exactly this algorithm will give you something faster than n log n. No one knows how to analyze it until now. It looks like a cute problem that you can try. Okay. Before I go to the next problem, question about selection. Good. So the next question that we can look at is a graph problem. So basically you have a graph, and the problem is to find an independent set that is as big as possible. So when you have a graph, and let's say you have a vertex set S, I said that it is independent if there is just no edge between any two nodes in S at all. Okay. So just to be more precise, give you some example. you have some graph, right? And now what I want is an independent set S with maximum size. That's the goal. For example, both of these are independent set in the graph because there is no, they are not directly connected to each other. This one is not independent anymore because of this edge. Okay. So this one is not maximum. This one might be maximum because, and I think it is maximum one, actually, I think. But it's not clear how to find one. And actually, it turns out that this is an NP-hard problem. So, question have you learned about NP-hardness in your previous class? Okay, good. So yeah, because of that, we don't expect to have polynomial time algorithm. We think as long as P is not NP, there is no polynomial time algorithm for any NP-hard problem. But it's not okay, it's NP-hard, we give up, right? We can try to, we need to solve hard problem actually always, and we can try to make it as fast as we can. By the way, about P is not NP, just to repeat what you have known, I think. Basically, everyone believes that P is not NP. Someone don't believe that, but it's just a few number of people. And if we are physicists, I think we would have declared as a law of nature already. But we are a math people, so we want to prove it. And this is really one of the most important scientific question that is ever asked, I think. So anyway, back to our problem, maximum independent set. Can you describe some very easy algorithm that at least gives you running time of 2 to the n times some polynomial factor? Yeah.
You can enumerate all subsets of V and then just check whether there's an edge between the vertices in this.
Exactly, good. You can just list all the possible number of subsets, all possible subsets. There are just 2 to the n many possible subset of vertices because there are n number of vertices. There are n vertices. For each of the subsets, you check if it's independent just by checking each pair. That takes polynomial time, n squared. And just return the maximum one. So that's n to the n algorithm. Well, what I'm going to do is to present you, again, a bad divide and conquer algorithm that gives you 2 to the n again. But once you see how to do divide and conquer, it's going to be clear, very easy to improve that. Okay, so let's say that V is just any vertex in the graph. Let's define n of V to be just a set of neighbor of V. All the nodes that are adjacent to V is a set of neighbor of V. That's NV. Okay. So now the idea is that if you pick any vertex V, there are really just 2 choices that you can make, right? Whether you want to include V into your solution or not. If you want to exclude V from your solution, you just exclude V from the solution. Well, then you just forget about V. And you can just recurse on G minus V. If you want to include V, well, you can. But now, what you can do is that you will recurse on G minus NV. So why do you need to why do I delete not just V but n minus n of V as well? Well, because if V is in the solution, you know that the neighbor of V cannot be part of the solution anymore, so you can just throw them away too. Okay. So yeah, this is the 2 choices you can make for any vertex V. If you exclude V, you just exclude it from the graph, recurse on G minus V. If you include it, just just know that you can exclude everything else that is adjacent to V2 and now recurs on G minus NV. Okay. So that gives you some recursive algorithm. That is, the algorithm given a graph is just to pick any vertex V, right? And then you compute S1, which is, you think of S1 as the best solution given that you don't have V in the solution. So that is just to recurse in G minus V. Otherwise, compute S2, which is the best solution that have V, and you recurse in G minus NV. Once you have computed two best solutions, whether V is in there or not, you just return the best guy among S1 and S2. Okay. And so this algorithm makes sense, it is correct. What's running time? Well, you can write the running time in this, like this, with this recursive equation. Like, given a graph of size n, you have two choices. And no matter what, you're going to recurse on a graph that have size at most n minus 1 because you throw away v. And the time outside recursion is like linear or poly n. And when you solve this equation, you get like basically 2 to the n times poly n. You can solve this by unfolding the equation, you get to the n. This is easy to see. Okay. This actually looks like a loose way to bound the running time. Why is that? Okay, because although like this guy have like n minus 1 nodes, it looks like this guy should have less than n minus 1 nodes, right? But it can be you can be unlucky, like a V can have no neighbor at all. Like V can just have degree 0. And then if that is the case, then even both of the graph have the same number of nodes, which is n minus 1. The question is, suppose you pick a vertex V and V have degree 0. What you should do about it?
Just including the solution and without deleting any other nodes.
Yeah, exactly. I mean, if V is a singleton node, you know that, okay, no matter what, it should be in the solution, right? So you don't even have a choice, just include it. There is no branching. So yeah, if the degree of V is 0, V must be in every maximum independent set. You don't have a choice. So actually, what you get looks like this. The running times look like if you pick a vertex V and it has degree 0, you don't have a choice. Just include it and recurse. So there is no branching at all. Right? There is no two term that you need to try and plus and sum them up. There's just one case. But if degree of V is more than 0, then now you need to try both of the case. But now one of this case, which is G minus NV, it must have at most n minus 2 vertices now, because you must delete your neighbor too. So now in this case, the running time looks like this now. Question about the recursive equation. Okay, so now you see that the second case just to dominate the first case, right? So you can just write down the equation like this. And now with some black magic that I'm gonna talk about soon, you can see immediately that you get this running time, which is faster than to the n. Super easy algorithm, but it is much faster than to the n. And with some more easy ideas, you can actually make it faster than 1.5 or even 1.4 n, 1.4 to the n. You can try this a bit, but yeah. Okay, so how did I do this? How did I get this immediately? So let me talk about it. How to solve linear recurrence. The quick way to do this is that like what I'm gonna do is I look at this equation, then I look at the largest root of this polynomial, that is the largest number r such that this polynomial is 0. This r is like, this r gonna look like a golden ratio thing, like something like this stuff. So r is basically less than 1.62, and then I just claim that theta of n is less than 1.62 to the n. So why? Like there's a reason behind this, but let me state the generic way to solve it first. So this is called annihilation method, and basically, if you actually have any equation that looks like a sum poly n plus a term here, which is n minus something, some constant. It's not like a some constant times n, right? It's n minus some constant. What you do, you just compute the maximum AI, and look at this polynomial, like r to the b minus summing over all I, r to the b minus ai. And you consider the largest root of this polynomial. Okay. So like I want to find r to be something that is larger. Okay, maybe I should say that let r be larger than the largest root of this polynomial. And then when you have compute r, then you just say that t of n is less than r to the n. So like there is a nice proof of this fact. And I would like to encourage you to try to look at this lecture note. Section 5 of this lecture note. Like there's like it's quite kind of nice. There's nothing deep about it. There's some math. But this is just a quick way for you. I just tell you the quick way, a quick trick for you to solve this equation. Why it's true, you can look up. But you see, like once you see this kind of equation, which is in the homework too, I think. Well, you can just here like b is 2, so I just consider r to the b minus this thing, right? And so this equation is just this equation. So I solve this equation. I get that r this number is larger than the largest root, and I just conclude this. And like this looks like a black magic, and like how do you even know that this is correct? Well, actually, there is an ultimate way to check, right? Like whenever you like if you guess some answer to the equation, to the recursive equation, or someone tell you that this is the case, although you don't know how that guy come up with the result, you can check just by induction, right? It just always work. Just do it by induction. So let's try to check that. Like, okay, we don't know how this is coming to you, but let's check. Like, we just use induction hypothesis to get this. Like, just apply induction hypothesis and you get this inequality. And we want to claim that this thing is actually less than 1.62 to the n. And now, what I need to do is just to show that this whole thing is greater than poly n, right? This is true if and only if like this thing is less than this. Only if and only if this thing is more than poly n. And to do that, just do some calculation, and it works out. So you are confident that this is actually true. Okay. Question about this? Okay, good. All right, so basically the point is whenever you analyze divide and conquer algorithms, you always need to solve recurrence. And there are a bunch of ways that I have actually shown in the class. Like I have shown you how to draw recursion tree and sum everything up through each level. How to unfold the equation by hand. I didn't talk about master theorem, but that's easy. Like you can look up. And also like there is a mechanical way to use this annihilation method. But the ultimate method that you can always use is guess and check. So yeah, like how to guess? Well, I don't know, but how to check? Just use induction. Okay, so like you will get homework on doing this. Okay, so today have a short lecture. So next time we're gonna talk about dynamic programming. It's gonna be fun and more challenging. Okay, more question before we stop for the day.
So on the homework, like 1A specifically, like it was easily solvable by the master theorem. Do we need to? Is that just a guess? Do we need to prove it by induction as well, or is the master theorem like enough?
You can use master theorem. That's fine. Yeah. Yep.
Can you talk about like why that equation works with the r to the b minus the sum of r to the b minus ai?
Like the proof behind this theorem, right?
Yeah.
Why it works at all. So okay. Let's see. Good. So the point is that let me tell you like some intuitive argument, not a proof. The proof is some math. It's not that intuitive to me, but you can look up. The intuitive explanation that I have is this. So what we want to find is just to find some, like first of all, like we first it's kind of, we can guess that whenever like the equation look like this, you're gonna get something that is exponential because like the size of the problem actually doesn't really reduce by any constant factor at all. So you guess that it should look like exponential time. So now it's just about what is the base R here that you want, that should make sense. And then, so if you guess that it should look like R to the n for some R now, you get like a poly n, and this is just the sum of I n to the ai. Okay. So now poly n here is just like kind of negligible compared to the exponential thing. Let me ignore that. Okay. And actually, so this looks like R. And basically we want to find like, we want that this sum here should be something that is less than R to the n, right? We want to find R such that this is true. And you can factor out, like now, if I just factor out a bunch of terms, you basically get that R to the max. Like you will get some factor that looks like this. Sum R to the bi less than R to the b times the same factor. Just factor something out and you will get like this term and this term and this term. So it means what? You want to find R such that this is true because this cancel out. What is the smallest R such that this is true? It must be like something that like larger than the largest root of the like this is now some now you see this is just the same polynomial here, right? And how does polynomial look like? It looks like when you plot a polynomial, it looks like this. Whenever R this is the largest root here, and you just choose R to be more than the largest root, and you know that this term now is gonna just dominate this term. Yeah, that's why how we get it. So it's intuitive enough, right? Yeah. All right, more question. Okay, see you next time.
We're struggling.
Yeah, no, how far did you,
Remember we both did exactly that at the end?
yeah.
One was like work on north or you want to get some lunch or something like that before we sit down and group.
Yeah, I do see I have the same, but I didn't want to do anything.
I just want to head down to Central instead. 3 should be fine, I think, each. Right, yeah, you have the later one. Yeah, sounds good to me.
I think the last game was
So I mean, we don't calculate all of the
I didn't know you
count the time in each of the
Expected value.
the whole thing.
Yeah, you just geometric.
When you count the whole thing, that's when I multiply.
I don't do much work on one test. Use the other method, like so this because this is all which makes it each be too loud. There's which is C, and since there are like log 2 to 12 and that